Welcome to Analyzing Quadratic Functions for Pre-Calculus of Math 11. And what we're taking a look at today is a section called Modeling with Quadratics. So it's really modeling real situations with quadratic functions. We can use quadratic functions to model many optimization. And optimization is really just a term used to say where we really want the best kind of output, best kind of outcome. So we're going to use this to model optimization problems. In particular, we can look at the vertex of a quadratic function when we are looking for a maximum or a minimum. So when we look for a max value, what we do is we take a look at the vertex, because the vertex is either at a peak or a trough. It's either a max value or a min value based on the quadratic. We can look at that point and figure out what is the optimal thing we're looking for. So in a lot of these problems, it's generally a good idea to draw a picture if you can. If you can't, no big deal, but usually drawing a picture helps. So let's talk about some of these steps for solving quadratic word problems. Determine the quantity to be maximized or minimized. And many times this is the last kind of sentence of the question. So look at that tagline. That tagline tells you what they want. Now, it's going to be an equation that they want. And what you should do is you should write this corresponding expression. Step 2 is identify the variables needed for the above expression. So you're going to create an equation. You need to know what variables are used for that. What has to happen is that when you create this expression, one side is the thing that you're maximizing or minimizing. That's one variable. The other side of the equation can only have one other variable. If there's two variables, three variables, there has to be more information contained in the question for you to get rid of that other variable. In this case, they're called related equations. Complete the square, identify its max or min. That's pretty straightforward. That goes back to what we've done. And make sure in the end you answer the question. So when I read this, two numbers are selected so that they have a difference of 12 and their product is a minimum. Okay, so what they want is their product is a minimum. So what we're trying to do is we're trying to minimize a product. Now product, what does product mean? Product's multiplication of two things. Which two things? Probably the two numbers. So the product is going to be x times y. And the p is what we're trying to minimize. Now, like I said before, we can only have two variables. P is what we're trying to minimize. And now we have two variables, x and y. So let's get rid of them. Let's see if there's any other information. Two numbers are selected so that they have a difference of 12. Well, if they have a difference of 12, that must mean if we take one and subtract the other, that's what difference means, it's got to equal 12. So we can replace, this is almost like a system of equations. We're not going to solve it like that, but we can replace y with what it equals. In this case, y equals 12 plus x. So let's take the p formula, which is xy. Let us replace y with 12 plus x. And what we get here is actually two options. We can either solve this using the factor intercept method and find the vertex that way using the average. That was basically what we did last class. Or we can do this by completing the square. So what I want to do is I'm actually going to do it both ways. Let me draw a little line down the middle here. Let me show you by completing the square. P equals x 12 plus x. If we expand that, we get 12x plus x squared. There is no constant term, so we don't have to worry too much about that. X squared plus 12x. Let me just rewrite it a little more familiar. Half the linear term, so the linear term is 12. Half of that's 6. Squared is 36, so we add 36. Subtract 36. We can complete the square. X plus 6 perfectly squared minus 36. So the minimum product is going to be given by this equation, depending on where the vertex is. If you look at this parabola, it is a parabola that opens up, telling us that there's a minimum. Where does that minimum occur is basically wherever the vertex is. The vertex is at -6 and -36. Therefore, x equals -6 is what we're looking for. Turns out that -36 is actually the minimum product. That's not what the question asked. And make sure you answer the question from there. Let me just show you that we can get that -6 the other way by using the 0 method. So if x equals 0, x equals -12, the x vertice, the x coordinate of the vertex is an average of those two, and we get, again, -6. So both ways we get an answer of -6. Once we've done that, we really need to plug that back in, make sure that we get the other answer. Y is 12 plus -6. That's basically just from the formula above. So y is +6. So make sure you answer the question again. The two numbers are -6 and +6, and that will give us a minimum product. This next question is a bit of a specific one. It's an optimization one where we're increasing and decreasing kind of two pieces of the equation. Lenny Leonardson has an ostrich farm. Every year he sells approximately 60 ostriches for the price of $200 each. So what I want to do is actually just set up the base case, like the starting case. The cost, the number that are sold, and the revenue. Now, how do we know how much revenue we have? Well, if we're selling at $200 a piece, I guess we could go cost in dollars, and we sell 60, well, that's $200 times 60 units, and that will tell us some amount. And it doesn't really matter too much that whatever the amount is, but in this case we see that it's a multiplication of the cost times the number that are sold. So now we're going to start doing a couple options. He knows that for every $5 decrease in price that he sells 2 more ostriches. Well, so let's do this. I just want to show you a table. We may not actually do this every time. 200 minus $5 means we increase by $2. So this would be 200 minus 5, 60 plus 2. We could do it again. 200 minus 10, 60 plus 4. You can multiply that out, see if it's actually doing better for us. But really what we want to do is we want to generalize this. So what we're going to do is we are going to let x equal the number of decreases. So the number of cost decreases in this case. So what happens to our table is we want to lose $5 a number of times, x times. But what happens when we do that is we gain 2 more sales x number of times. And what happens to our cost index, or our revenue, is 200 minus 5x, and 60 plus 2x gives us our value. So what we're trying to do is we're trying to maximize revenue. And the revenue in this case is 200 minus 5x, 60 plus 2x. So a little bit of a specific type problem. You really need to maybe look over this a couple of times, figure out how to set this up. You can really expect this kind of question in class. I'm going to solve this using the factor 0 method. It's typically a little bit easier, I think, in this case. Completing the square on those two factors is a little bit ugly. 200 minus 5x equals 0. 200 equals 5x. And 200 divided by 5 is 40. So we get an x value of 40. 60 plus 2x equals 0. 2x equals -60. X equals -30. So those are the two zeros. That doesn't tell you the vertex, the x-coordinate of the vertex. We still need to do kind of like an average. Let's go -30 plus 40 over 2. -30 plus 40 is +10 divided by 2 is 5. So what that means is we should have 5 price decreases. Now, I don't know what the question asked here. What was it? What is Lenny's maximum possible revenue? So let's talk about this. His revenue, we can just use the revenue function, is 200 minus 5 times 5. So we're just slotting in that value. 60 plus 2 times 5. And 5 times 5 is 25. So that's $175 we're selling each ostrich at. And we have 70 units sold. Multiply those two, and we end up with $12,250 for the maximum revenue. We could take a look at some of these other totals to make sure that they are actually below that revenue. 6 times 200 is going to give us 12,000 here. So we see already that because our original was at 12,000 and our maximum revenue here is at 12,250, we did see a bit of an increase. Good luck on some of these word problems. If you run into problems, go back, try and break it down a little bit, and we'll have plenty of time to talk about this in class.